Hello everyone, so today we are going to be learning a super important concept in math called prime factorization. Okay, but before that, let's recap something called the Fundamental Theorem of Arithmetic. If you have watched my video on fun facts about prime numbers, you should know what this is. But it doesn't matter, I will still go through what this is if you. So, the fundamental my writing so messy. This is the fundamental theorem of arithmetic. Now it states that any composite number I can take any composite number from the world, any composite numbers, and I can definitely express it as the product of some prime numbers. Now I'm just gonna give you an example. For example, okay, so wait, what? I'll give you an example. Okay, I'm gonna give you a super simple example. Let's say I have the number 154. I could express it as a product of prime numbers. Okay, so this number would be 2 times 7 times 11. See, this number is a product of, when you multiply this, you get 154. So basically, a fundamental theorem of arithmetic states that you get any composite number, you can definitely be able to express it in the product of prime numbers. See, all these are prime. Okay, so today we'll be learning prime factorization, which is essentially how to take a composite number and then break it down until it is made of a prime product. What do I mean? Basically, you just learn how to take, like, for example, just another number 154, how to know that it is 2 times 7 times 11, and there's only one variation of this product. That means there's no other set of prime numbers that can give you this. Alright, 154 equals 2 times 7 times 11. There is no other set of prime numbers that when you multiply you also get 154. So it's like the unique. This is the prime. These are all prime factors because we know that each of these are factors, right? So they're all prime. So that's why we call them prime factors. Okay, so that is unique. There's only in 154 only these 3 primes when multiplied together you get 154. There's no other primes that when you multiply you get 154. So today we'll exactly be learning how to get a random number and instantly, not instantly, but you have to work it out, express it as a product of some prime numbers. And this is the process called prime factorization. So we'll be learning how to do prime factorization today. And just in case you're scared that you may, forget some stuff, I will also be releasing a practice video to make sure you guys understand how to prime factorize. Okay, now, there are 2 methods for prime factorization. The first method is called the ladder method. The second method is called a factor tree. Now, the more widely used method is the ladder method, but I will still teach you the factor tree. But whenever I'm going through prime factorization questions, I will always do ladder method. Okay, so I suggest you guys learn ladder method, but if you want to learn factor tree, is fine as well. I will still go through that, but most of the time I'll be using ladder method. So please make sure you stop though lah. Okay, so now you get any composite number, right? So I'm just going to go over here to the random number generator. Alright. As you can see, the minimum is 1, the maximum is 10,000. Okay, so eventually it could be any single number, but if it's prime, then we'll do it one more time. Okay, but I will just randomly generate a number and we'll use that number as an example of how to prime factorize. Let's go. 2537. Okay, so just now I searched up 2537, is it a prime number? Apparently, it is not a prime number, it's a composite number, but it's kind of stupid because miraculously the number that we generated was these 2 numbers. Okay, I'm not gonna use this kind of examples because I want examples with like some 2s and 3s. I don't want the big numbers because big numbers really takes a lot of time to find out. Okay, so I will not be going through this one because this is a bit too big. I mean, I didn't want this, so let's go ahead and generate another one. Okay, let's go. 5008. Okay, I think this one's manageable. So basically, a ladder method is you just gonna draw a ladder. Okay, I'm gonna show you what I mean. Okay, so I'm pretty sure all of you know what a ladder is, right? You basically have like these things, you have to climb it up, right? It's not the same thing in math. You literally just draw a ladder, okay? But it's not exactly a ladder that looks like this, okay? I will teach you how to do it. Okay, so 5008. What are you gonna do firstly? Okay, this is basically how I'm gonna give you a little structure of how the ladder method works. So basically, you have your starting number, which I'll mark it over here. Starting number. Okay, ST, no. Starting number. Now, starting number. And then what I'll do is, this is going to be a structure. It's going to look something like this. I know this doesn't really look like a ladder, but you can sort of picture how it's going to be a ladder. Like, whoa, you know, like all these things, like, you know. Like, you can sort of picture like the ladder thing, right? I don't know. Okay, but whatever. So, how it's going to work? You're just going to pick a prime number signifying a p. I'll just put a p over here. You're gonna take this original number and you're gonna go divide by this prime. Okay, and once you divide by this prime, your result will be of this next rung of this ladder. Okay, so you will get the next number, which I just write number. Okay, because of course we don't know what it is. Then you will divide it by another prime number. You get the next number. So you divide by another prime number. Divide. Until eventually, the result, when you take this number, you divide by the prime, your answer is also a prime. Now, of course, if it's also a prime, you can't divide anymore, right? So just now, how the ladder would have looked if I did 2, 5, 3, 7, it would have looked something like this. And this is such a bad example, right? So which is why I didn't want to use this example. Okay, I don't even know why we so coincidentally got this. Okay, but anyways, you get my point. So basically, you have the original number. You're gonna start dividing it by prime. Divide. Now, basically, what's gonna happen is that all of these, this, when you multiply them, you are gonna get back this starting number. Okay, so it's basically like your prime factors. Because think about it, guys. You have your starting number. What you do is you keep dividing. So it's like you have this starting number. I'll just say A. You're gonna divide it by 2, divide by 2, divide by 2, and you get 2. So can I just say that 2 times 2 times 2 times 2 equals 8? Right. A, you go divide 2 equals 2. That means 2 times 2 times 2 times 2 is 8. Right. Same logic for any other. Same logic. What is it? Okay, same logic for any other ones. If I have x, I go and divide, let's say 3, and after I divide 4, I divide 7, and I get 2. Then we can say that 3, 4, 7, 2. Right. So that means we can confidently say this. Right. So same logic for the prime factorization ladder method thing. In this case, you can see the starting number, right? The starting number. You divide by prime, you divide by prime, you divide by a prime, you divide by a prime, and you get this prime. This times this times this times this times this back to the starting number. So that's exactly how it works, alright? I hope you guys can picture what I'm doing. So just that was our number. 5008, right? So I want you to pause the video, alright? Try to work this thing out yourself, okay? So basically the rules of this is you're gonna take 5008, you're gonna draw the letter, right? And you're gonna start dividing by prime. You make sure that this number you put here is a prime, because if you're gonna put like a 8 here, okay? And 5008 can divide 8, by the way, just so you guys know. This is valid, okay? But the problem is, you sort of don't want this. You don't want this thing. You don't want this. Why? Because this is not a prime. If you're just going to put it like that, then you might as well say that this is not a matter of prime factors, just factors, right? You might as well not do that. So, you better put an actual number. The most common one is a 2, because 2 is a prime number, remember? If you divide, you can work it out, you can get 2504. Okay? Now I'm using a calculator to do this because I don't want to do long division. Okay, but of course, if you have no calculator, right, you're like maybe in an exam, like they tell you must do long division on the paper, then of course you must do on the piece of paper, okay? But this one's pretty easy, like mentally you can also do it. 5000 divided 2 is 2500, and after that 8 divided 2 is 4. Okay, so actually there's no need for calculator in this one. Okay, now this one can still divide another 2. Okay, and of course you can say, I can actually divide 4, you know. I know you're being smart, but don't try to cut corners because we are doing prime numbers over here. So just take 2504 and go ahead and divide 2. 1252. Aha, I can still divide 2. Now, of course, if straight off the bat you see a number that you know that, oh, it can divide. For example, like if you're like this very good guy, you're like very smart, right? If, for example, you're supposed to like prime factorize 208, and you like have a lot of brain cells, right? You are, I mean, like revising the multiplication timetable of 13, and you know that this divide 13, and you know 13 is yes, you can do it straight away, okay? But if you don't, then you just do 2, because in the end the result will be the same. As I said, guys, there's only one single unique set of numbers, set of prime factors that can form a certain number, that can be a product of this certain number. So that is why there is only one single unique kind, which means that there is no way there's a lot of different answers. When if I tell you to prime factorize 5008, no matter who does it, we'll all get the same answer in the end. We will all get the same answer in the end. We will get the same prime factors if you do it correctly. Just that sometimes our orders may be different, right? I'll give you an example. I'll give you my 208 example just now. Some people can decide to do 208 divided by 13 first. Right? 16. 16 divided 2, 8, 2, 4, 2, 2. Right? There you go. But some people, actually I'm supposed to do this lah. Some people want to do this. There will be 104, 52, 26. Notice how the results are still the same. 2 times 2 times 2 times 2 times 13. In this case, it's just the reverse. 13 times 2 times 2 times 2. Now, let's say that over here you decided at 52. 52, you know that you can divide 13, and you decided to put 13. Then over here, you would have gotten 4. And you have divided by 2, and you would have gotten 2 again. So you see how it's all just the same no matter what you do. So that's my point. The result will ultimately be the same. And that's the crazy thing about the fundamental theorem of arithmetic. Right? The fundamental theorem of arithmetic states that any composite number, it can be expressed as prime factors, and that's exactly what we're learning today, how to do this. And understand that every number has a unique set of prime factors, and you cannot change it, it's always the same. Okay, just the order may be different. Okay, so 1, 2, 5, 2. Let us go ahead and divide 2 once more. Now, this can be divided by 2, 3. Now, here you face a problem where you cannot divide 2 anymore, right? But are there any other prime factors you can possibly divide it by, or is this a prime number you can just stop here? So, you, at this point, at this juncture, it's sort of like a juncture where you think, is 313 a prime number? Can you divide it by, anything else, right? Can you continue on? So sometimes you just have to think about it, okay? Sometimes you need to think about it when you're doing this kind of question. So it's not just, you can't really just do it mentally. You can't just say, 5008, I can straight do it mentally on the prime factors, okay? Because sometimes you need to think, what can I divide this by, and what's the result that I divide it by? Okay, so it's 313 prime. Okay, so actually 313 is prime. Okay, so I also did not just like know it was prime straight away. I had to sort of think through it. Okay, anything divided 313, I found out it's actually nothing just now when I paused the video. I thought of it and there's nothing in divided 313. Then you know. So in this case, your answer would be, you see, for example, they will usually phrase a question this way: express 1008 as a product of its prime factors. Right? So you will answer 2 times 2 times 2 times 2 times 313. Actually, there's actually something you do, the 4 twos. You must do index notation. But I'm not going to teach you that for now. I will teach you that later in this video, but I want to go through some more examples. I want to go through at least 2 more examples of this so that you guys are really sure on how to do this. Then I'll teach you index notation, how to express your answer, because it's going to be very important. You can't just leave it as 2 times 2 times 2 times 2. Right, that will be annoying. Right, the examiner will be like, I don't even want to mark this, girl, bro. Right, it's like so weird. Okay, so now let's go ahead and generate ourselves a random number. Let's see. 9029. Okay, this is just interesting. I'm mumbling so much. Okay, so is this prime? Firstly, if it's prime, there's nothing much to do, right? But I'm pretty sure it's not prime. But of course, you can see that it cannot divide 2, so you need to actually think about this, right? Firstly, divide. Can you divide by 3? No, you cannot, because you can do divisibility test, which is why divisibility test is also something like this. Not this too messy, which is something that's so important. Can you divide 4? No, of course not, because the last 2 digits. If you don't know the divisibility test, doesn't matter, you can go watch my video, okay, about divisibility tests. Okay, but it's not that, but you guess, but it's a very good method here that you could use, possibly. Okay. Actually, I'm not sure if this is a prime or not. Okay, guys, this is a bit annoying. We are getting another prime. Oh, this is so annoying. Okay, guys. Okay, so what do we do? Okay, so random number generator, guys. We have to do it one more time. 7674. Okay, this one seems promising. So let's go ahead. I'm pretty sure there's no need for us to say it's divide 2, right? But we'll get a little problem because this number we cannot do a divide 2 anymore. But guess what? If we add up the digits, 3 plus 8 is 11, 11 plus 3 is 14, 14 plus 7 is 21. And what's 21? It can divide 3. Therefore, it can divide 3. Right? If you don't understand what I'm trying to say, doesn't matter. It's divisibility test, okay? It's not necessary. Divide 3, so you get 1279. Nice. Okay. Can this be divided by anything? Of course, it cannot be divided by 2. Can it be divided by 3? If you add up, you get 19, and it cannot be divided by 3 as well. Can it be divided by 7? No. So just think about it. Can it be divided by anything? Okay, I was a bit too lazy, try it out one by one, and apparently this is prime as well, so I have no choice. We are gonna be stopping that. So it'll be 2, 3, 1, 2, 7, 9. Okay, these examples so far have been a bit too bad because there wasn't really a chance for us to really go through a very good wholesome example. So I'm gonna make one myself. We're gonna forget about random number generator, right? We're gonna make one myself. Okay. I'm gonna make one for y'all to do. It will be a bit interesting. Okay, let's try this one. 6, 4, 6, 8. This one is a good one. Straight off the bat, we can do divide 2. Right? There'll be 3, 2, 3, 4. Then you can straight away tell me you can divide 2 again. Which actually, if you guys know, there's actually a little trick. You can just split this up. 16 and this one 7. If you divide 2 here, divide 2 here. But it doesn't work all the time, so you cannot just like rely on this method. It's a little trick for y'all, but it doesn't work all the time, so don't just like, oh, if I'm 9, 9, 9, 9, I want to divide 2. This side divide 2, this side divide. No, do this. Okay, but this number can't even divide 2 anyway, so. Okay. So, this one, divide 2, you get 1617. And you notice that, oh no, we cannot divide 2 anymore, but is this prime? It is not prime, because you can realize that it's actually divisible by 3. So we get 539. That's the interesting part. Can it divide 3 anymore? Cannot. Think about it. What are the other primes? 5. But this, of course, this can be divided by 5. 7. Let's try it out. Divide 7. If you do a long division, you notice that this actually can be divided, right? So, in this case, 77. So, 7, 77. And the first thing you will notice straight away is that this can be divided by 7 again. You get 11. 11 is prime, so that's where it stops. So this is an example of a good prime factorization that I like. A good ladder I like, because you can clearly see that there is a lot of different variations of prime numbers. Okay, yeah, so 2 times 2 times 3 times 7 times 7 times 11. This is actually not a good way to express it. I will explain index notation later. Okay, now let's do factor 3, but I'm going to use the same example this time. Okay, wait, just the example, I forgot myself. It was 6, 4. What's the example I gave just now? 6, 4, 6, 8, right? Yeah, 6 more 6 8. I nearly forgot, so forgetful. 6 more 6 8. So if you don't factor 3, I'm not gonna give you examples of this because this is not really a good method. Or at least a method you should be using because I don't suggest this method. I suggest the latter method. It's a more commonly used method. Basically, you just do a factor 3 like so. And why do you call it a tree? Because it really looks like a tree. You understand what I'm saying? So you split it 2 and another number. So like ladder method, but the express is shown in a different way. This is 3 2 3 4. Now you're just gonna branch it out like so. And every time you branch it out, these primes, you don't just stop it there. Okay, you are still gonna do branching out of this prime. So you just do it like this. Okay. So we are gonna have to minimize this a lot. Okay. Hopefully you guys can see. Okay, this 1617, as we have gone through just now, can divide 3. So that'll be 3 and 500. Oh, sorry. 539. So this one will be 2, 2. Okay. 539. Remember, we could divide 7. So 777. 3, 2. Okay. 77. It'll be 711. Okay, and that's where it stops. So you can see what factor 3 is. And if you look at it, oh, sorry. If you look at it, it actually really looks like a tree, right? If you visualize it properly, like you're some artistic guy, like the tree, a tree. You can see how, it is like. Alright, so now let's try another example, but with 72,072. Okay, it's gonna be a bit more satisfying because the tree will look bigger, right? We're just gonna do one more time. This is the most obvious thing you can do, alright? So 72072 divide 2, you'll get the most obvious thing, 36036. This one divide 2, you get, I'm pretty sure you guys know. Oh, sorry. 18018. What's my pen doing? Okay. Then you can make this into 9009. Actually, no space there. And remember, for factor 3, you must make sure you branch everything out like so. So, like that. Okay, 9009. Okay, my one doesn't have space anymore. Okay, but 9009, by the way, you cannot divide 2, so that's sad. But what can you do with 9009? You can actually divide 3 because, 9, you can get my point. 3 and 3003. And these things just gonna go back here. Okay? It's a bit squeezy, but let's continue. Now, 3003, obviously, you can still divide 3, you can get 3 and 1001. Okay, now 1001, just so you know, it's actually 7. Alright, 7. Now, after you work it out lah. Wow, so you know actually no space, but lucky you are finished because there's 11 times 13. The rest drop out. Now I'll teach you index notation. Okay, so now we're done with factor 3. Let's learn index notation. Okay, guys, so firstly I want you guys to understand the concept. Okay. Exponents. You understand this concept, yeah, pretty much set for index notation. Exponents. Okay, now 2 times 2. Now if you know what is exponents, then you can just like skip this part. But if you don't, then make sure you listen. 2 times 2 equals to 2 squared. Guys, 2 times 2 equals 2 squared. Now you probably say it's because of 2 and 2. Okay, but that's a bad example. Sorry. Okay, if I have the number, I'm just gonna say 63 times 63. It's actually just 63 squared. And just so you know, this little thing is not called 2, right? We call it squared. Okay, so that's basically exponents. So now, why do we put a little 2 on there? It expresses how many times this thing is being multiplied by itself by. So if I have 2 and I keep multiplying it by itself for n times, that means I can actually express it as 2 to the power of n. Get my point? So basically, must know this. Okay. This is the number that's being multiplied. This is how many times it's being multiplied by. So now let's go through this. 63 times 63. This is first time that's getting multiplied. This is second time that's getting multiplied. So it got multiplied a total of 2 times. Actually, this is like, basically just do a counting. 1, 2. So 2 times. Which is exactly why they put a 2 over here. So same logic. Okay. If I have any number and I multiply it by itself another time, then there'll be a total of 2 numbers, alright? Now, don't confuse this with adding. That means if I have 63 plus 63, that is 63 times 2. Not 63 squared. Okay, not this. It's 63 times 2. So, 63 plus 63 is 63 times 2. 63 times 63 is 63 squared. That means you multiply by yourself. Okay, that means you don't multiply any number. If it's 63 times 62, then you don't have to put any square. But it's by multiplying by itself. Okay, so now, if I multiply by itself thrice, that's like 3 times 3 times 3. So you can count. Let's do I'm counting 1, 2, 3. So then you just have a 3 and you put a 3 over here. And this is we call cube. Okay, so now you can also call it 3 to the power of 3. Okay, that's what I said just now. Okay, so basically, if I have something like this, I have a and then the b over here. It's basically just expressed as a to the power of b. Basically, it's just expressed as this. A, and after that you have this thing, a to the power of b. As easy as that. Okay, but if this small little number is a 2 or a 3 as special names. So in this case, just now the one I showed you, it has a 2 over here. If it's a 2, then it will be called squared, because it's like a square, right? When you want to find the area of a square, you basically take this side times this side, right? And we know square are equal. All the sides are the equal length. So you're basically taking this number and you're multiplying by itself again to find the area, right? And why is it called cube? I'm pretty sure you can guess. When you have a cube, you'll find the volume is basically 1 time, 2 times, 3 times of the same number, because it's a cube. So that's why we call it that. Okay, try to reference it. So listen, guys, listen up. When you have a number, you multiply it by itself. Right? You have a number, you multiply it by itself a certain number of times. So you basically just put this certain number of times over here. So it's expressed as a to the power of b. Okay. So if I have like this, I'll say 3 to the power of 4 is this. 2 to the power of 2, this. 6 to the power of 7, this. 4 to the power of 5. Okay, but as I said, this you can also express it as 2 squared. Because I told you if there's a 2 over here or a 3, if it's a 3, it's special case. You guys, this is squared, this is cubed. Okay, but of course you can also call it 2 to the power of 2 lah. So you get my point? Now that you know what exponents are, when you get your answer, alright, for example, I get my answer, this is my answer. This is my answer to the question, right? Like after I finish prime factorizing, this is my answer. You don't express it this way. You do what I told you. Exponents. Like so. 1 time, 2 times. So express it as this. Then if there's nothing, you just put it here. Now, of course, you can also put like 7 to the power of 1, 11 to the power of 1. But 7 to the power of 1 is just 7, 11 to the power of 1 is 11, so there's no point. Okay, so basically, this is called index notation. Basically, wherever you are told to, like, for example, prime factorize a number, and they tell you to leave your answer in index notation, you better not be like, you better not do this. Better not do this, guys. Leave your answer in index notation means, what is index notation even? Means that you must express it in this way, which means that you must have all these things going on. Okay, if they see something like this, alright, then you're cooked. You cannot do that. Okay, so basically, index notation is very important. Index notation basically means that you must express it in this way. That means you have all these powers whatsoever, these exponents. So I'm gonna give you another quick example. If I have something like this. This is gonna be a very big number, okay, but what if I have this? Simple 1, 2. Express the index notation lah. So after you finish prime factorizing it, you will get this. But you don't actually write it like this, right? You have to do what I'm trying to do right now. 1, 2. This is 1 time. This is a total of 4 times, so it's 11 to the power of 4. This is 3 times, so okay. Right, so that's it for today's video, guys. Hope you liked this video. If you have any questions, you can drop them down in the comments below. I will be sure to answer them. I can guarantee that on my video, my channel. Alright, I will answer them definitely. Okay. So hope you guys like this video. Please consider liking and subscribing with it. And that's all for this video. Peace.